How much it's redshifted is also something to be noted. It is not random, but is directly proportional to the galaxy's distance from us. So it's not just a random, oh, everything is redshifted, most things are redshifted, and it's random. No, how much it's redshifted is proportional to the galaxy's distance from us, which is pretty crucial and pretty interesting. And again, of course, we have to thank Hubble for figuring out these distances. That the figuring out the distances itself is not trivial. Sometimes the distances he estimated had to be kind of updated, especially for some special kinds of galaxies like active galaxies. But overall, it's a lot of work to even figure out the distances, okay? So, in other words, the farther a galaxy is. So, we will look at, so by the way, I didn't show you the 3 pictures. Here is the Big Bang to Big Crunch, just Big Bang and then expansion, and then Big Bang and then expansion at a rate fast enough to avoid recollapsing. So, third kind of solution in which the universe is expanding only just fast enough to avoid recollapse. In this case, the separation shown in this last thing that I showed also starts at 0 and increases forever. However, the speed at which the galaxies are moving apart gets smaller and smaller. The speed at which the galaxies are moving apart gets smaller and smaller, although it never, Newtonian dynamics was sort of the main thing that described such things. And then we now have also general theory of relativity, which is an updated theory for gravitation. But, unless you need the accuracy of relativity, you might be fine with just Newtonian mechanics. It still stands and it still does a great job in most cases. But because of its deterministic nature, it led people to think that being deterministic is normal. Being able to just predict something deterministically was expected and what people thought was basically right until we came across quantum mechanics and its developments in the 20th century. So let's see. Laplace suggested that there should be a set of scientific laws that would allow us to turn those equations into relativistic equations. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. He basically took quantum mechanics and introduced relativity to it. He basically wrote down the relativistic equations, relativistic version of the same equations of quantum mechanics. It explained mathematically why the electron had spin 1/2, that is, why it didn't look the same if you turned it through only one complete revolution. But did if you turned it through 2 revolutions. So it also predicted that the electron should have a partner, as in the way in which alpha particles, which are positively charged particles given off by radioactive atoms, are deflected when they collide with atoms. At first, it was thought that the nucleus of the atom was made up of electrons and different numbers of a positively charged particle called the proton, from the Greek word meaning first, because it was believed to be the fundamental unit from which matter was made. So at that point, they were like, oh, maybe proton is the fundamental unit. This whole discussion about quarks that we will get into, we still had not discovered quarks, right? We just barely discovered the electron and nucleus and all that. So, however, in 1932, a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle called the neutron. So every body attracts every other body with a force that is proportional to the mass of each body. Thus, the force between 2 bodies would be twice as strong if one of the bodies had its mass doubled. This is what you might expect, because one could think of the new body as being made of 2 bodies with the original mass. Stephen says the red moon is tomorrow. I was wrong. I liked. Thank you, Stephen. Thank you for sharing. John Foster says, oh, I missed it. I can't wait to see my special video with my name in it. Now we will continue on to the second chapter, which is called Space and Time, after I take some sips of my water. How are you doing? Hey, hello. Hello, everybody. How are you doing? This is a live. This is not a premiere. It's a live. It's not a short. It's a live. It's not a video. It's a live. It's not a premiere. It's a live. We're going to be live for a few hours now. And welcome. Welcome, 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 welcome. It is just me right now, but I know and hope that many of you will be joining very soon here. Very soon here. The kitty cats are with me. Suji Mama has gone upstairs to hunt. Baji Baba and Fuji Baba are here down here with me. And I have Stephen Hawking here with me as well. Brief History of Time. His book is here with me, even if not him. And I just want to say good evening, good morning, good afternoon, good night to everybody. We are live. We're live. We're live. We're live. Let me pull this a little closer. Koto. I don't know what that means, but hola. Hello, my friend. Mike D, hello. Reno, Nevada. I see. You're giving me suggestions for the meet and greet. Reno, Nevada. Okay. Cooper says, can I get your number? Can I? I really want a girlfriend. Okay. So now I will share the live because I always forget and I currently also forgot. Absolutely amazed at everybody who joined, and thank you so much for joining and welcome to this excellent live. We will talk about brief history of time and physics and cosmology in just a second here. I always try to say hello to everybody. I guess for a trip a while ago. I've only been once, and I did sort of like the canyon tours. It looked so different. So Nevada actually sounds good. California also sounds good. I really want to go to California and see some more things. On one side of the partition, one places a source of light of a particular color that is of a particular wavelength. Most of the light will hit the partition, but a small amount will go through the slits. Here's the picture for that. See? Slits, light, all that. And it makes a pattern on the screen behind. Now suppose one places a screen on the far side of the partition from the light at half the distance. This law predicts the orbits of the Earth, the Moon, and the planets with great accuracy. If the law were that the gravitational attraction of a star went down faster or increased more rapidly with distance, the orbits of the planets would not be elliptical. They would either spiral into the sun or escape from the sun. Name in it. Steven, I don't know if it's I don't know if it got posted today or in a couple of days, but there's going to be a video with your name in it, with the video title having your name in it. So because you are such a good special student of mine in these lives, we're all students,